It is an immense pleasure for me to welcome you to this special colloquium inserted in the webinar series of the Graduate Program in Physics of the Federal University of Pará in Amazônia, Brazil. I ask everyone to kindly leave the microphone and the camera turned off, except for the moment you're going to speak. Questions will be allowed in the end, unless otherwise requested by the speaker. The questions can be asked using the chat, both in this virtual room and in the YouTube. Today, we have the great honor to listen to Professor Reinhard Genzel, who was awarded with the 2020 Nobel Prize in Physics, together with Andrea Ghez and Roger Penrose. Professor Reinhard Genzel was born in Germany. He received his PhD in physics and astronomy in 1978 at the University of Bonn, with a thesis in radio astronomy prepared at the Max Planck Institute for Radio Astronomy at Bonn. He is a honorary professor of physics at the Ludwig Maximilian University in Munich since 1989. At the University of California, Berkeley, in the United States of America, he was a full professor at the Department of Physics and Astronomy from 1998 to 2016. In 2017, he became professor of the graduate school at the UC Berkeley. Our special guest is a fellow of the Royal Society and is presently director of the Max Planck Institute for Extraterrestrial Physics in Munich, Germany. Apart from the Nobel Prize in Physics, Professor Genzel's research has been honored with various prizes and recognitions, including the Otto Hahn Medal in 1980, the Balzan Prize in 2003, the Shaw Prize in 2008, the Crafoord Prize in 2012, and the Tycho Brahe Prize in the same year, and the Harvey Prize in 2014. A 40-year journey is what Professor Genzel will tell us about today, and I should not make you wait longer to listen to him. Professor Reinhard Genzel, thank you very much once again for having accepted our invitation, and from this moment on, the audience is yours.
Well, thank you, Professor Crispino. It's a great pleasure to be here and there, so to speak. I'm in Munich in the winter, and you're in Amazonia, and I'm sure it's pretty warm there. And what I am planning to do is to tell you about a trip which my research group and I have been undertaking for the last 40 years in various ways to test general relativity and also at the same time the so-called massive black hole paradigm by observations of increasingly sophistication and resolution in the center of our Milky Way. Now this research really, you should see it as a fairly obvious part of a bigger picture, which is the testing of general relativity and the probing, the understanding of a number of rather bizarre, you might think, spectacular predictions the theory has had. Now, if you go to that, then this story is really a 100-year journey. Of course, I only participated in sort of a little less than half of it. That tells you the dimension of this kind of work, and it'll be going on for many more years, I'm sure. So Einstein published his theory of general relativity and the fact that one could make a geometric theory of the structure of space-time, which is created by masses, as you see on the right there, in 1915-16. And already 1 year later, Karl Schwarzschild, in the trenches of the First World War, found the first solution of a problem for the theory in the case of a mass which is spherically symmetric. And in this first theory already, in this first solution, the theory predicted what we now call black holes. I'll explain to you what that entails. But now it went on, and there was more work to be done, which went on for the next 50 years. More complicated solutions were found, for instance, solutions for rotating black holes, which were found in 1963 by Roy Kerr, and also Roger Penrose, who received the Nobel Prize with me and Andrea Ghez last year, added to this tremendous building of the theory by showing that these solutions which Schwarzschild and Kerr had found, these black holes, were not just mathematical fairy tales, so to speak, but should and could occur in the real universe. So what is a black hole? Well, the key element, or one of the key elements of the theory is that masses, like for instance the sun in this picture, distort space-time surrounding it. And any other object, any other mass, whether with mass or without mass, which would be a photon, has to react to this space distortion. Now, for the sun, we know that if you were to take a rocket at the surface of the sun and let it escape, shoot it away from the sun, then you have to speed it up to about 600 kilometers per second. For the Earth, the same number would be 11 kilometers per second. But that is dictated by basically the fact that the sun has a certain mass and a certain size, so the surface gravity of the sun has a certain value. Now, if you, in your mind, you make the sun more compact at the same mass, then the velocity of escape of your fiducial rocket changes. In fact, if you compress your imaginary sun to a size of 3 kilometers, then the speed of the rocket is 300,000 kilometers per second, and that's the speed of light. Now, I told you that light itself, of course, sees gravity as well, and is the fastest communication we know of in the universe. So if even light cannot escape, well, then what you would have to have is a region which is decoupled from the outer world, so to speak. No signals, not even light, cannot be sent from this innermost region within this region of 3 kilometers in the case of the sun, which we call then the event horizon. So that's the first prediction of this theory. Rather bizarre, but understandable if you're willing to understand, number one, that the maximum speed of communication is that of light, and that photons also are affected by gravity. Now, there is another prediction of the theory, which is still more bizarre, if you like, and that is, in the theory, if you were now take the rocket and not fly outward, but inside towards this inner region, then you would not be able to turn around anymore. And in the finite speed of time, finite time, you would end up at the very center. So anything which falls into the event horizon, therefore makes up the mass of this object, according to the theory, is located at the very center in a region of zero extent. And that is a density singularity, so infinite density. That's remarkable. And in fact, that's part of the theory which we have not and likely will not be able to test because of the communication barrier, but which is fascinating for many ways, because it's quite possible that that's where the theory is not correct. we do not have a theory for gravity on the smaller scales where quantum effects would become important. And many physicists are, looking at black holes as, so to speak, the atoms of gravity to understand how a quantum theory of gravity would look like. Okay, so that's a short introduction to black holes. Now, I told you the first solution in 1916, then Kerr's solution in 1963, but really up to the up to the 60s, there was no example. Astronomers, for instance, would know about such objects. So the question is, are these bizarre objects of relativity realized in the universe? And then within only a few years, indeed, two types of candidates were found. One were very bright sources of X-ray radiation, which the X-ray astronomers found in our Milky Way, many of them, in binary objects. And in fact, the picture we now have is that there is a stellar black hole and a more normal star, which are bound in a binary system. And the stellar black hole is the result, the ashes, if you like, of a very massive star, which came to the end of its life and didn't produce any energy anymore. And so it collapsed in the end to a black hole. The other discovery which was made was that of quasars, and that I come to next, which are the discovery of massive black holes. Now, a very fundamental question, of course, is how would you how would you be able to study such black holes if they really do not emit any radiation? And for that, I'm using the analogy of the solar system, where again, the sun is in the middle of the solar system, and the planets, as we know, are orbiting on quasi-circular orbits. And Kepler's laws tell us that the outer planets are moving more slowly than the inner ones. So now if you, in your mind, switch off the light of the sun, what would happen then? Well, the planets would still revolve on their orbits around the sun, because it's about gravity and not the light of the sun. So turn that around. If you now think that Tycho Brahe and Kepler would have analyzed such a system, they would have had to come to the conclusion that there is in the center of the solar system an object with one solar mass, which is, basically causing a perturbation of the space-time such that the planets move around in circles. So that's how we can actually make black holes visible, if you like, by their action on other particles. So I mentioned the second type of black hole, which I will talk about for the rest of this talk, and these are massive black holes, objects which we now know are at the centers of Milky Ways, including our own. They were discovered also in the 1960s by radio astronomers when they were discovering in Cambridge, England, for instance, new radio sources which did not have very bright, obvious counterparts in the visible. And one of these sources is this radio source 3C273, which Martin Schmidt, an optical astronomer at Caltech, then observed with the Palomar telescope in the optical, and found that the counterpart of the radio source was what looked like a very faint compact star. You see these spikes there, faint compact star, but in the spectrum, in the optical spectrum of the optical emission of the star, he found emission lines of very well-known elements, hydrogen, helium, and neon, and so forth, and but all redshifted by 16%. Now, at that time, of course, Hubble in the 1920s had found the expanding universe, it was well known that redshift could be caused by just the expansion of the universe, and the further away an object is, the faster it moves. Now, a redshift of 16% in the 1960s was unheard of. Nowadays, that's actually a fairly nearby object. At that time, that was a sensation because the distance you calculate from the expansion curves is 2.4 billion light years. So that's a significant fraction of the time over which the universe has been expanding. So if you put an object at 2.4 billion light years, then this little star which you see there actually is very, very luminous with a luminosity of 1,000 times the entire Milky Way. So how could you possibly generate that much energy? And so there was a discussion in the 60s over several years how you could explain these quasars. And it became very clear that it couldn't be ordinary fusion from hydrogen to helium like in stars. Also, one discovered that many of these quasars had variable X-ray radiation and even gamma ray radiation, so very highly energetic particles and photons, and also often collimated beams of very fast radio jets expanding away from the center of these galaxies. So a number of theorists working on this problem then proposed paradoxically that black holes could be the source of these quasars. So how would you think of that? Well, if you have a black hole and now material falls into the black hole, then we learned already that, of course, inside of the event horizon, no more radiation can escape. But on the way into the black hole, just outside of the event horizon, the gravitational energy, which is released easily and turned into heat, can then lead to a lot of radiation. So that's the black hole paradigm, the massive black hole paradigm. Quasars are powered by the accretion of mass, gas, and also stars onto massive black holes with masses of millions to billions of solar masses. So how could you prove that? Well, Lindenbell and Rees wrote a very famous paper in 1971 where they basically said, well, okay, at the distances of quasars, billions of light years, you cannot possibly make a measurement like I described to you with test particles. That's too far away. And it would still be actually too far away. So how could we find something which is a black hole and yet it's nearer to us? And so Lindenbell and Rees speculated, well, maybe these black holes reside in other galaxies as well. In fact, we now know that almost every galaxy has such a black hole. And the bigger the galaxy is, the bigger the black hole. So Lindenbell and Rees said, well then, maybe even our own Milky Way might also have such a black hole. So that was the beginning, if you like, of the phase in which the astronomers now started coming in and began to test that proposition, starting in the 70s and until the present time. So the Milky Way then is sort of the most obvious candidate because it's so much closer than quasars, by a factor of tens of thousands closer than quasars. But there is one problem. If you fly in from the outside of the Milky Way where the sun is, into the center, you see these dark smudges. That's interstellar dust particles between the stars. And as we fly here into the center, this dust extinguishes the visible light by a large factor, such that optical radiation does not easily get to us from the center. So we have to go to wavelengths where this is not the case, like in the infrared, longer wavelength radiation, radio radiation. and also X-rays. So nowadays we know that in the center of our Milky Way, there's a very dense star cluster, which in this picture here on scales of light years are the blue points, very dense, about 1 million times denser than in the solar neighborhood. And in the very, very center of the Milky Way, there is a compact radio emission structure with a compact radio source we now call Sagittarius A star, which is this little red-white point which you see in the center. Now surrounding that, in addition to the stars, there's also gas, ionized gas, which you see in pink, and neutral gas in green. Now, in Berkeley, Nobel laureate Charlie Towns, who had won his Nobel Prize in 1964 for the invention of the maser and laser, in his later years moved to California and then started doing astronomy. And he had equipment, spectrometers, to look in the mid-infrared at spectral lines of ionized neon, which come from these pinkish streamers, interstellar clouds of ionized gas. And he and his students, you see John Lacey is one of them, but many others, then in the 70s started measuring the Doppler motions of the ionized gas. I then joined as a postdoc in 1980, and we extended the studies to the green stuff, to the neutral gas. And by looking in different spaces, we could basically map out the motions of the gas clouds and found that they move very, very quickly in the innermost region, much more quickly than you would have expected from just the stars. So we felt quite assured by 85 when we wrote a paper and sent it to Nature that within a few light years, the mass was dominated not anymore by the stars, but by an object which had a mass between 2 and 4 million solar masses and was very compact. So you see this in the bottom right there, that if you plot the mass on the vertical axis, and then in logarithmic units, the distance from the center of Sag A star, that as you go to a very large distance, the mass changes. That's the extended star cluster. But when you come inside of about 1 parsec, or 3 light years, the mass really doesn't change anymore. And so this could be a black hole. But must it be a black hole is the question. Could there be alternatives? And indeed, there were lots of alternatives. In addition, many people were skeptical that the gas motions were a very good way of tracing the gravity, because gas can be pushed around by magnetic fields, can be pushed around by stellar motions and stellar winds, and so can't really be sure. So many people were skeptical of this conclusion. Also, 1 parsec or a few light years, which is the innermost region you can track with these motions, is 1 million times the event horizon size of a 1 million solar mass black hole. So in order to really be sure, what we have to do is we have to, number one, go further in so that we are sure that this mass really is compact. And we have to have better tracers. To go further in fact, the radio astronomers used intercontinental interferometry, very long baseline interferometry, to measure the size of the radio source at different wavelengths, which is depicted in the left curve there. These red dots are different measurements with VLBI at different wavelengths. And what one finds is that the radio source is the smaller, the shorter wavelength you measure. Nowadays, we can measure this in the millimeter range with VLBI in the millimeter range, and there the size of that compact radio source is a mere 40 microarc seconds. 40 microarc seconds. That's incredible. I mean, we human beings have a resolution with our eyes of 40 arc seconds. So that's a factor of 1 million times smaller in size or angle than what we can resolve with our eyes. If you put 10 microarc-second object on the moon, then it has the diameter of a euro cent coin. Okay, so that gives you sort of a feeling of the dimensions of these black holes when you put them far away. But clearly the radio astronomers with these measurements already fairly early on in the 1980s, 90s, ongoing to the present period, have been making ever more refined measurements showing that this radio source is compact and is really not moving in the very center. The second condition I mentioned is to measure not gas but stars, because they're a much better tracer of gravity. So when I moved in 1985 from Berkeley to here, to the Max Planck Institute, and became director here, we undertook a major instrumentation program geared in this direction of measuring the motions of stars, among other things, in the infrared with ever better resolution. And so that required a lot of technology, low noise imaging detectors, for instance. Then what we call adaptive optics, which is basically a method to correct the distortions the Earth's atmosphere does on the light. Here you see the waves are coming in, and then the Earth's atmosphere and the winds are basically distorting the waves. And if you then make an image, you get a smeared out image. And to correct that, we use adaptive optics. There's a mirror, as you see, which we can deform to undo what the Earth's atmosphere has done and generate a flat wavefront. And then we get the sharpness of the waves as well as you can from the diffraction limit of a telescope. Now, another thing is to, of course, go to very big telescopes. That gives you better resolution. And finally, if you want to do this technique, you need to have an object, a star, which is bright enough and close enough to the source you're looking at, such that you have a way to analyze the light in the way I described to you. Not always is that the case. In fact, very rarely is that the case. So modern telescopes are nowadays equipped with what we call artificial laser guide stars. So we make a laser at the sodium D line. That's why you see this orange light. And we shoot that up in the sky to an altitude of about 90 kilometers, where in the upper atmosphere, meteoroids, which are coming into the Earth all the time, basically get destroyed and form sort of a thin layer, few kilometer layer of atomic material, amongst which there's sodium. And the sodium then we can focus the light on, and the sodium backscatters the light back to the telescope and acts as an artificial star. So the progress in the field, with other words, very much depended on a lot of new technology, which over the years we and others have been able to apply, and therefore get ever better in terms of the specificity, resolution, sensitivity, etc. of the measurements we can make. Now, by the 1990s, then we were already then using a 3.5 meter telescope and using not adaptive optics at the time, but so-called speckle imaging, to look at the motions of the stars from year to year to year. And in this picture on the right, you see the location of Sagittarius star is the green cross. Then the circle is a diameter or a radius of 1 light month, a half an arc second. And red, green, and blue are images taken over 3 years. And you can see that near Sagittarius star, there is a star which clearly moves. Further out, you see the star images are white. So that means they don't move very much. Well, okay, that's exactly what you would expect if you have a central point source and Kepler's laws are working for you. Kepler's laws, which tell you that the nearby stars, which is the innermost stars, moves fast, and the outermost stars move slowly. By that time, in the mid-90s, when we had the first results of these measurements, a second group had joined using a big telescope. The first one of the 10-meter class telescopes, the Keck telescope. There was Andrea Ghez with her colleagues, Eric Becklin, Mark Morris, and others. They too had an infrared camera which could use these speckles, and they too carefully measured the motions of the stars. So we published our first results in 96, there in 98, but the impressive thing is really we found more or less the same thing, which is that inside of about, well, 10, 20, 30 arc seconds, the motions, the mean motions of the stars increased with the Kepler law, which is what you see there. Outside is sort of a mishmash of more or less constant motion, but then inside of about 10 arc seconds or 30 arc seconds, the motions increase exactly with square root of the distance, 1 over square root of the distance. And the mass you would get out of this are about 3 million solar masses. This is roughly the same mass which we had found a decade earlier, okay? So indeed, the gas motions weren't that off as many suspected. So clearly, that looked pretty promising. But now let's ask the same question we asked 10 years earlier. This could very much be a black hole, but must it be a black hole? Now the innermost stars, they are on scales now of about 10 to the 5 times the event horizon size. So it becomes a little more difficult to think of configurations other than a black hole, which would fit in there. One such configuration would be a possible speculative cluster of neutron stars. Neutron stars don't emit much, so they are faint. You wouldn't see them in optical pictures, yet they are fairly heavy on stellar dimensions, so they could sink in the cluster to the center and thereby look like a compact source. There are other options which you think of, but the question is, so how would you prove that right or wrong? Well, you have to go closer. You have to go closer, and that was the second obvious thing to do. You have to go away from the statistical technique we were using at the time. See, here we are measuring the average motion of a bunch of stars, and from that we are sort of making a model of the source. We're assuming that the stars are distributed in an isotropic fashion with a certain density distribution, and the mean motion then can be related through Kepler's laws to the mass. That's a somewhat uncertain thing, plus you need a lot of stars to make it very precise. Much better would be if you could measure not the motions, but the actual orbits of stars. So both groups, the Keck group as well as our group, started thinking about that, and we were pretty convinced if we could measure better with more precision, introduce on the 10-meter class telescopes adaptive optics, which has allowed us to see more stars. Maybe we could see stars which have short enough orbital motions that we could, short enough periods that we could see these periods. And indeed, nature was very, very good to us. Within a few years, both groups found stars which are so far in that their orbital periods are only tens of years. And one star, which I'll tell you more, which is the best one we have, in fact, is on an elliptical orbit. And that elliptical orbit has an orbital period of 16 years. There it is. This star, S2, made its first close-by motion around the black hole in 2002, at which point it moved about 8,000 kilometers per second, so more than 200 times the speed of the Earth around the Sun, at a distance of about 3-4 times the Neptune orbital radius. So we are on scales of the solar system. So if you turn that into a measurement of the mass, 8,000 kilometers per second at 3 or 4 times the Neptune radius, then you come up again with 4 million solar masses. So obviously, the same mass which we had seen 20 years earlier with the gas motions, and then 10 years earlier in this statistical motion, was entrained within 17 light hours of the central radio source Sagittarius star. 17 light hours is about 1,000 times the event horizon size. So we really have come far in now, and hardly any other option other than a massive black hole is possible. And again, very important, both groups saw that. There's different instruments, and they found the same results. So that within a few years, in fact, most everyone in astronomy, and then also the physicists, became aware that we were moving toward a fairly definite proof that such massive black holes exist as predicted by general relativity. And indeed, if you think of any alternatives, there are some speculative alternatives, but not much possible. So by 2017, we had excluded everything within about 100 times Schwarzschild radius, all these other options which you see, stable astrophysical star clusters, also some speculative things like fermion balls. All of this could be excluded from the measurements. The only sort of speculative object which people brought up was a so-called boson star, which was sort of a speculative conglomerate of, if you like, Higgs bosons, which is not quite a black hole, but is somewhat extended. So it's just a little bigger than the event horizon of a 4 million solar mass black hole. Unfortunately, if you take such a boson star and you have some baryons fall onto it, like happens in the galactic center all the time, a boson star pretty much, after a short period of time, collapses to a black hole. So it's not a very likely, but it's certainly a possible solutions. So that was the state of affairs in 2017. So let me raise the same issue, which I've done before now. This looks pretty good. At that point, we could say there must be a black hole beyond any reasonable doubt, but as long as general relativity holds, because these other alternatives there are excluded because we use general relativity to exclude these options. So does general relativity hold? Now, obviously the star, when it came to us first time, 2002, we knew, oh, this star is going to come back 16 years later to 2018. And so we felt, okay, if we are ready by 2018 with a still better measurement, maybe we can test general relativity in this extreme regime where nobody has ever made tests. And indeed, we have a tool. We have 4 telescopes. So this is the Paranal Mountain in Chile, where ESO has its 4 8-meter class telescopes, which are these 4 big domes, one of which we used for our measurements. But from radio astronomy, we know that you can combine the light of telescopes and thereby generate, basically through interference, a still bigger telescopes. So this is the way it works. You basically take 2 telescopes, say, here come the light waves from your distant star, and now you bring the light from the primary and secondary mirrors and bring it together in an interferometer, make an interference, and that allows you to generate basically a virtual mirror of the diameter of all the telescopes, which in this case is 130 meters. So that's 20 times bigger in size, and therefore 20 times higher in angular resolution and astrometric precision. So in 2005, we proposed to ESO, let us build that thing. Let us build a beam combiner, which allows us to make this measurement, a very precise measurement of the orbit of S2 when it comes back in 13 years or 12 years when we made the proposal. And indeed, gravity was built, and we were ready in time to install it on the mountain in 2015, led by a fantastic team of experimenters from institutions in Germany, another Max Planck Institute, and the University of Cologne, two observatories in France, in Paris, and in Grenoble, then the observatory in Porto and Lisbon, and ESO itself. And it took more than a decade, but gravity was ready in time for the Parry approach. To show you how difficult that is, we made a little movie which we call the torture of the photon in its last millisecond. So here you see the photon coming in, hitting the primary, secondary, and tertiary of one of the telescopes. Now, you have to bring down the beams into the Coudet room, so there are lots of mirrors. Unfortunately, we do lose quite a bit of light there. Once you end up in the bottom there, then you analyze the wavefronts. And here is where we basically have our deformable mirrors and correct the wavefronts with adaptive optics. Then the beams are brought together in a tunnel underneath. In the tunnel are little carriages which you must use to compensate for the geometric path lengths and correct that to the first order. Then the four beams from the four telescopes come into the lab, and now coming into our instrument where there are no more vibrations. It's cryogenic, so the temperature is low, no more heat radiation generated. We can manipulate the images at will and actually extract on the sky two beams, one beam from a bright star near the source and one beam on the source itself. We can adjust the beams. We can also rotate the beam direction, also in preparation for making the interference between the different beams. It's very efficient and without using much space if you then go from free optics into monomode fibers. So here we are now and bringing in the four beams in fibers. We need to still correct for some residual phase corrections which hadn't been corrected earlier. That is done by stretching and pulling on those fibers. We're also correcting the polarization through torsion of the fibers. And then finally, after all of this manipulations, we can bring in the four beams into a microchip of about 1 centimeter size, where we can combine the four beams of all the telescopes. So if you have 4 telescopes, you can make 6 combinations, and then you sample the delays 4 times. So we come out in with 4 beams, come out with 24 samples, and then you put this all in a spectrometer and onto a detector, which in fact does not have any noise anymore. So we don't add any instrumental noise. So that was quite a feat. And Frank Eisenhower, the PI, and his team really have done a terrific job. Frank just got a big prize for this from the European Astronomical Society, the Tycho Brahe Prize. Okay, so here we are, ready for the star. And so when the star came, we were able to measure the motions and the orbit very, very well, much better than we had before. So basically the measurement with adaptive optics are in black from the years before, and the measurements with gravity are the blue measurements. much more precise by about a factor of 10 or more. Also, it's very interesting that when you look at the central region with adaptive optics, which is the second image to the right, there are many other stars, of course. But with the interferometer, which only looks at a very small region, you don't see the confusion of these other stars. You only see the star S2, and that's the very good thing, you also see Sag star itself. So that means that the measurement then near Peri is a very simple triangulation of directly measuring the phase difference between the waves on S2 and Sag star. So then during the Peri year, which you see in the center there, we could measure with this precise high precision tool the motions of the star every day, not every month or every year as before, but every day. These are the red points to high accuracy. Of course, we also would have a spectrometer on the mountain Symphony to continue to do the spectral measurements so that we have both motions on the sky, two motions on the sky, as well as the spectral dimension, which you need to fully determine the orbit of the star. So that's what we had, and then we started measuring, and indeed, we were able to see several effects of general relativity. The first one, very famous one, is so-called gravitational redshift. That's basically the finding that near masses, the clocks are going slower, and the light rays which are emitted from such a region are slowed down to or pushed to longer wavelengths. The next effect which is predicted is that the orbit doesn't close anymore. So in Newton, unless you have other objects nearby, you have closed orbits. Not so in general relativity. The orbits precess, that's called the Schwarzschild precession. In fact, that was one of the things which made Einstein famous within a year of the theory, because he predicted Mercury's orbital precession. And then finally, we knew that there were emission variations from Sag star itself, constant variability, which may be suspected to come from hot gas right outside of the event horizon in the so-called innermost stable orbit. So in the period between 2017 and 2020, early 2020, before the observatory unfortunately had to be shut down because of the pandemic, we were able to measure all these effects. And you can see on the left side, the Newton orbit is the gray line at 0, while general relativity is the blue line, and then the red points are the data points. So we clearly have detected this gravitational redshift with very high precision, very high precision. Likewise, the orbital precession, the Schwarzschild precession, in Newton, the star would go along at 0 there at this dashed dotted line, whilst the precession predicted by general relativity is this kink, which happens near Peri, and indeed exactly how we see it. And the angle is 12 arc minutes in the case of S2. And then finally, these motions around the black hole we saw in so-called flares when Sag star is very bright, happens rarely, but in 2018 happened 3 times, and we could see motion of this hot gas right around the innermost stable orbit, where the predicted motion would be about a third the speed of light, and that's exactly what we saw. So when you look over this period of the last 40 years, we started in the 80s by having the first indications from gas motions, by seeing that there were very fast gas motions at about 1 million times the event horizon. We've taken a long trip, really, through several generations of instruments to push by about 1 million in angular dimension from the 1 parsec region where you could see the effects of the black hole all the way to the region around the event horizon, which we can see with radio astronomy techniques as well as with this hot gas and showing that indeed the mass must reside within a few times the event horizon size. So must it be a black hole? Well, it's now clear that general relativity applies, and it's very likely that indeed this is what we would call a Kerr, Schwarzschild Kerr black hole. But to really be sure, we have to go one step further, and I'll tell you about that at the very end. There's a second dimension to these measurements, which I want to at least mention, and that's the astrophysics. I mentioned to you already that these black holes are common. In fact, they're very important in the evolution of galaxies. Every galaxy seems to have such a black hole, and at least for the more massive galaxies, like elliptical galaxies, these black holes are, because they are fed and are active as quasars, have a lot of influence on the evolution of the galaxies. So the prediction you would have of such a black hole, if you put it into a galaxy, is that a so-called cusp of stars forms around it. I've depicted this here. You can see in the center is your black hole, and then a cusp of stars would form over time. Takes a long time, about at least millions to billions of years until you would form that. But then you should see old stars, stellar black holes, and also neutron stars sort of peaking in their density around the big black hole. So one of the questions you could, of course, raise is what we've learned from our measurements and Andrea Gez's measurements about this astrophysics of a nuclear star cluster around a black hole. And it's rather surprising that many of the predictions which had been around before these started turned out to be wrong. The first one is this cusp of old stars, which on the right side is this line, this dark line, which was predicted to be there. What we see is that the old stars here in green and also red are fairly flat. They don't really peak in the center. However, there is a peak, which is this blue distribution. That's exactly the young stars. It's not old stars. It's young stars which somehow make it into the very center. Absolutely not expected. Because these young stars are only tens of millions of years old, and so they couldn't possibly have migrated slowly into the center as the theory would have predicted. The next thing is that I told you that we have seen the Schwarzschild precession, just as Einstein's theory predicted. Well, in turn, of course, that means there cannot be much mass surrounding the big black hole. Because if there is a lot of mass around the big black hole in form of another big black hole, say, so a binary black hole, or an intermediate mass black hole of 10,000 to 100,000 solar masses, or even many stellar black holes, well, then that would counteract the Schwarzschild precession and would show up as a retrograde Newtonian precession. And in fact, in this diagram, where there is the mass on the horizontal axis of such possible other objects, as well as the distance from the center, you can see that with gravity, we basically can now exclude a second black hole in the center below a few hundred to maybe a few thousand solar masses. So that's very important, because such secondary black holes would be very, very interesting for the future, by measuring the in-spiral of such objects into a big black hole, which you could see with gravitational waves. The European Space Agency, ESA, is planning a very big, important mission called LISA, where such in-spirals may be observable and thereby help us to, again, test general relativity. So this is just one example. Another one is that you wouldn't expect to see any young stars because stars form from clouds, from interstellar clouds, and in this innermost region, the tidal forces from the black hole, the big black hole, is so large that you would not expect gas clouds to collapse and form stars. Yet, when you look and check it out, in the central parsec, there's almost 200 O and B stars. So stars which are young and have masses between, say, 15 to 100 solar masses. That's extremely surprising. How is that possible? Well, we think it's possible because from time to time, gas clouds, big gas clouds, fall into the center, and then they get basically shocked and pushed and so forth. Initially, they can't form stars, but over time they cool, get more compact, get denser, and then at some point they can form stars. And indeed, the stars we see seem, at least the biggest ones, seem to reside in a disk. That's what you exactly would expect, a disk, a rotating disk of stars, which probably once was a disk of gas. So in other words, this trip had some interesting additional elements of surprise about the astrophysics. There are more I could tell you about, but I don't have the time. So let me come back to my eternal question at the very end and ask, are we done? You might get a little impatient with me and say, my God, how far does a guy want to push? Well, as physicists, we have to really make sure that we have tested a theory to the utmost limit. And general relativity says that the mass and the angular momentum, the mass m and the angular momentum a, the spin of the black hole, are the only two numbers you need to determine a Kerr spacetime. There's also the charge, but let's forget about the charge. So mass and spin are sufficient. No other numbers are needed. So for instance, the quadrupole moment of a Kerr black hole, Q, is determined by m and the spin a. No more freedom there. Also the octopole moment, etc., etc., etc. We call that the no-hair theorem. Black holes are very simple. They don't have structure. That's true only in general relativity. There are other theories of gravity where that is absolutely not the case. So that's why what we would like to do next, already now and next, is to show that this nuisance parameter epsilon there is zero. That's what general relativity would predict. No hair. Now we know already some things from X-ray spectroscopy. The X-ray observers have set a limit of epsilon of a few in some nearby active galactic nuclei. The in-spiral of the stellar black holes in the LIGO event in 2015, which led to the 2017 Nobel Prize, sets a limit on epsilon of about 0.3 to 0.5 or so. Our gravity hotspots set a limit of 1. So that's pretty good. So that in that sense, all these measurements are consistent with general relativity, but they're not, significant to the extent that you might not worry. So the red possibilities tell you what we are planning for the future. The radio astronomers want to see the so-called photon orbit. The innermost stable orbit for photons would make sort of a shadow around the big black hole, which the radio astronomers have seen in 2019, not in the galactic center, but in M87, which you see in the upper left. And they very much hope to see it in Sagittarius star this year. And if you could combine their measurement, they would see the same thing as you see up depicted up on the left side there, and you measure the size of the ring and take the very precise measurement of the mass we know from our stars, you could push the limit of epsilon to 0.3 or 0.1 even. If there were a pulsar in the central region, which so far has not been found, but people are looking very hard, you could also go down to 0.1. ESO is building, and we are building for ESO, an instrument for the next generation big telescopes called the ELT. The ELT has a 40-meter diameter, and so there we could push that epsilon to 0.05. And then finally, an in-spiral of a stellar black hole into a massive black hole, observed by LISA, which I mentioned already, with gravitational waves, would be the ultimate to test. Now, of course, we don't know what these tests will show. Will they show that general relativity is correct to all these orders, or will we possibly at some point begin to see deviations, say, due to the quantum nature? Well, that we will have to wait for another 40 years, maybe. It won't be me who's doing this, but it's been a very exciting 40 years to trace the story of massive black holes and in the galactic center. Thank you very much for your attention.
So, Professor Genzel, we thank you very much for this wonderful webinar. And before we proceed, I would like to ask everybody that's listening to you to turn on their microphones for a huge round of applause. Okay, so we already have some questions that I will pass them to you. But before that, and while people get inspired for another questions, let me give you, as I said in the beginning, an overview of the audience you had. That is you have had more than 100 people listening to you, if we count together the people that are participating in this room and in YouTube. And they are from essentially all around Brazil. So all the 5 regions Brazil is divided in. So states like Amazonas, Pará, obviously where we are, Tocantins, Roraima in the north region, Bahia and Rio Grande do Norte, for instance, in the northeast, Mato Grosso in the center west, Minas Gerais, Rio de Janeiro in São Paulo in the southeast, and also Paraná and Rio Grande do Sul, about 5,000 kilometers from where I'm speaking now, right? So
fantastic.
we have had obviously our personnel, right? Undergraduate, graduate students, postdocs, teachers, and professors from the Belém campus of the Federal University of Pará, like Danilo Alves, Jaime Urban, Jorge Cacineiras, Newton Barbosa. But we have Pará is a huge state, right? It's bigger than some of the European countries, right? The smallest ones. So we have people from other cities than Belém, like Abaeté, Capitão Poço, Castanhal, Marabá, Santarém, Salinópolis, like Caio Macedo and Carolina Benoni, that work with black hole physics as well. And we have not only people from physics, but also from geophysics, like Cícero Regis from UFPA, and people from chemistry. We have had also students, undergrad and graduate students, scientific initiation, postdocs, teachers and professors from other universities, institutes, observatories, and research centers all around Brazil. Just to mention some of them, like Álvaro Nogueira from Rio de Janeiro, Douglas Continho from Paraná, Eduardo Simões from Tocantins, João Braga from São Paulo, José Nogales from Lavras, Minas Gerais, Kepler Oliveira from Rio Grande do Sul, Leonardo Brunet as well, Nelson Studa from São Paulo, Nelson Yokomizo from Minas Gerais, Satis Kuma from Unirio, and Wilson Zanquin from UFABC. Also people from abroad, like Olivier Sarbach, that I believe is attending us from Mexico. So thank you all for attending. And now let's move to the questions. So the first question I have registered here comes from Satis Kuma VH. I don't know if he wants to make the question himself, although his question has been partially answered along the talk. But Satish, do you want to make the question yourself?
Yes, thank you, Luis. Thank you, Professor Genzel, for a thorough talk. Like Luis said, you kind of answered all the questions I had in mind, but I'll make very precise questions. First of all, the talk was very thorough, and especially I enjoyed the part of the photon torture, right? I never thought telescopes are so complicated as particle accelerators. Thank you so much for the thing. So the first question was about the precision of the nearest star, right? The one with the 16-year period. You answered that question. It has like 20 arc seconds per 15 years or so, right? Has this been measured for the other stars? That's my first question.
Well, okay. I mean, I think we of course, for the adaptive optics measurements, have a field of view which allows us to take in all the central stars. So we have currently, both groups have orbits for about 50 stars, which is very interesting in itself, because again, there's the astrophysical part of all of this. What is this? The question I raised is, how did these stars come in there? And of course, for different theories, how the stars would come in there at different orbits. But for the GR part of it, it's really about stars which make a close peri, and the gravity measurements can really only be done on one star at a time. So we had to do the last years around the peri of S2. Of course, we have devoted more or less solely to S2. Now, as we speak, we will have one more star which is about to come in for another peri this year, and another one in 2 years. So there will be continuous possibilities, although these stars are not as bright and as ideal as S2. But more importantly, the next big thing we want to do is measure the spin of the black hole. And to get the spin of the black hole, we need to measure the lens steering precession. The lens steering precession is equivalent to about 0.4 arc minutes, and that we cannot currently measure on S2. So we need there a star. We've basically simulated that with marked orbits. We need a star which is about 2 or 3 times further in. And so that likely would be a very faint star. And so the interferometry which we were doing is indeed spectacularly sensitive. I mean, it's 1,000 or several thousand times more sensitive than what people had done previously. So we are hoping that if there's a star inside of the S2 orbit, we might get it. And then within a few years, we would be able to measure the spin. But okay, that's, again, we're dependent on nature. Laboratory physicists can construct that. We cannot. We have to, we have to hope that nature gives us the tools.
Thank you so much. Perfect. The second quick question is about that shooting laser thing. It's cool. What is that for? I did not quite follow that.
Okay, so in order to make the correction with adaptive optics, you need to have a point-like source near or on the source you're likely you want to study. Well, the star S2 is actually a fairly bright star, 14th magnitude, but it's not bright enough to lock the adaptive optics loop on it. So we would never be able to do AO or interferometry on it unless we have a star which is brighter than that by at least 3-4 magnitudes. And so in that case, if there's one in the galactic center, which in fact there is, we can do this correction on a nearby star. But in most of the other objects we are studying, there are no such stars. And so then the laser stars is a method to generate a star wherever you like by focusing the sodium light into the upper atmosphere and use the backscattering, the resonant backscattering in sodium D from the atoms of sodium up there, which travels through the atmosphere and basically gives you a tool to sense the atmosphere.
Thank you so much. Thank you, Luis.
Okay, thank you, Satish, for your questions. Thank you, Professor Genzel, for your answers. So next question now comes from Douglas Coutinho, Federal University of Paraná. Douglas, do you want to make the question yourself, or do you want me to read it for you? Okay, then I'll read it. He has written, it was mentioned that ionized gases in near circular orbit might not be a proof for the existence of a black hole. Magnet field could also be a possibility. My question is, what would be the possible origin of the magnetic field? Also, that would give higher speed at smaller radius as well.
This is a very good question. In fact, I have not touched on that part of the object story at all. Yet it is likely in the next years one of the more spectacular side of the story. You would expect ab initio that in the high energy environment of a black hole, near the outside of the event horizon, of course, but inside of the innermost stable orbit or around there, to be very strong magnetic fields. The magnetic fields would, so to speak, be anchored inside of the black hole and would be one vehicle to extract energy. As you know, the Penrose mechanism allows in a rotating black hole in the so-called ergosphere to extract energy, rotational energy out of a black hole, and the mechanism likely is magnetic fields. So think of it basically, there's a dipole magnetic field, for instance, anchored in the black hole rotates, and that field now is sort of jerking around the gas on the outside. And this interaction can lead to energy acceleration of gas, like making these flares, which we are seeing, also polarizing the vacuum and generating very high energy radiation like gamma rays and so forth. So the entire energy creation of quasars is likely connected to black holes. Now, we have been able to see, in fact, the magnetic field in this innermost region now through this hotspot. And the incredibly exciting story there is that if you think of an accretion disk, and you look at it face on, so you have it rotating on the sky like this, then the Stokes parameters, vertical and horizontal, should occur twice. All right, so that means that the Stokes parameters should rotate with a rotating disk twice as fast as the particle orbits. And what we see is that the rotation of the polarization, but at the same speed or the same period as that of the gas motions. That's terribly exciting because that tells us that the field is not in the plane of the accretion disk, but probably perpendicular to it. And that, in fact, has been something which Roger Blandford has proposed for quite a while as a mechanism or as an indication of very strong fields, so that basically a magnetic field dominated plasma, which is very efficient in generating jets. So you see, I mean, we are getting into the plasma physics of the high energy phenomena around black holes here.
Okay, so thank you, Douglas, for a question. Thank you very much, Professor Genzel, for your answer. So the next question comes from Professor Kepler Oliveira from Rio Grande do Sul. Kepler, do you want to make the question yourself?
Yeah. Yes, please. Thank you very much, Professor Genzel. Excellent talk. And my point is for you to please reinforce the need for technological developments for basic science. Our government has always been very lean on funding science, and when you showed the gravity equipment, it was very clear that it required a lot of technological development. So could you please just reinforce the need?
Yeah. Well, Kepler, look, I can, vis-a-vis your government, for instance, I'm as you might imagine, as a Nobel laureate, you're all of a sudden being thrown into the pot of people who have to go out of their room and talk to politicians, and that's what I've been doing, of course, for the last half year. And indeed, I might recommend to you the story of the maser and the laser. Charlie Townsend's work is really absolutely a super example of where you can demonstrate that Charlie was not interested in producing a welding machine or a scalpel for surgery. Absolutely not, or a clock or something like this. No, he wanted to have a lamp. He wanted to have a lamp to study molecules. Now, Towns has written a beautiful article in annual reviews for astronomy and astrophysics a while back, maybe 10 years ago. He passed away 5 years ago, but 10 years ago, he wrote this article in very layman terms, basically showing how the laser turned from this sort of solely curiosity-driven approach into something which benefits human mankind in such a broad swath of applications. But that you cannot turn that around, where you basically say to a person of that quality, forget about your molecules, okay? Instead, invent the laser for whatever application. That's not how it goes.
Thank you, sir.
So thank you, Kepler, for your question. Thank you, Professor Genzel, for your answer. Now we have a question from an undergrad physics student. It's Caio Raw. Caio, do you want to make the question yourself, or do you want me to read it?
Yes, please. Hello, Dr. Genzel. Thanks for the excellent talk. I would like to know what advice would you give to an undergraduate physics students looking for a scientific career in physics, and what kept you motivated, and would you make something different?
Yeah, well, okay. I mean, that's depends on what you're interested in, okay? I'm not sure, to tell you the truth, I would nowadays go into astronomy. Astronomy has developed enormously over the last 50 years in ways which are spectacular. Unfortunately, the kind of astronomy which will dominate the next 20 years is not exactly what I personally am interested in, and that's exoplanets. Okay, we're doing it actually with gravity. The gravity turned out, we didn't expect that, to be the best spectrometer for looking at the atmospheres of exoplanets. And that's one of the fields which will explode now in astronomy. On the other hand, I mean, obviously, looking at the Big Bang, for instance, is a field which will be very likely ever more interesting. But there, the worry I have is the number of people. Also gravitational waves, because I very much support gravitational waves, but 3,000 people work with you, and is that if you like that, no problem, but I wouldn't. I'm very much more comfortable in a modest group. I mean, of course, initially we started in groups of a few, Nowadays, the Gravity Consortium has 50 people, so that's still manageable. But 1,000, nah, too much. And the other side is, you know, what drives you? Are you interested in computing? Clearly, astronomy in the next decades also will be dominated by big surveys, going ever deeper in the large-scale structure of the universe and cosmology. So if you're good at that, that's a very fertile region. I'm not so good at computers, okay? So another reason for me to not do that. I would go into neuroscience, but you know, it depends on tastes of people. Most important of all is do whatever you find exciting. If you want to do research, and if you want to do it like I have done with a lot of fun, you must really like it. This is not a 9-to-5 job. This is something which you must burn for.
Okay. Thank you, Kai, for your question. Thank you, Professor Genzel, for your answer. Well, I have, in fact, myself, some questions that I would like very much to make to you. But obviously, being the person that is controlling, I mean, I must control myself at first. But maybe let me take this opportunity to ask a couple of questions. Well, when you mentioned the young stars around the central black hole, right? You mentioned also that are some other surprises other than that. Would you be so kind as to mention at least one of them? I mean, which were these other surprises that you came through along your research?
Yeah. Okay. I mean, obviously the star formation. I mean, you look in all textbooks of the 80s and 90s and 70s and whatever, and you would learn that black holes should be surrounded by a vast desert of old home folks and some neutron stars. Okay, stellar black holes, and not these O and B stars. So the story is clearly that we learned that a n-body system with 1 million stars and a black hole has many more freedoms. And there are timescales which we never would have dreamed. And there are fast trains with timescales of only, you know, I would say 1,000 years or 100 years, which generate pathways of bringing stuff surround in this cluster over large scales, which nobody had thought about. The other side of this, of course, is that astronomy for the star formation issue, astronomy, of course, has been always dominated by the thinking that gravity is a weak force, and you know the time scale which dominates everything is the relaxation time scale of distant two-body interactions in gravity. That's absolutely not the case in the center of a big with a big black hole, because the black hole forces all particles surrounding it like lame ducks on these Kepler orbits. And so that means that their interaction, if they're close together, is much stronger. So there's a whole lot of rich phenomena which we had not been dreaming of back then. Another one is, of course, the destruction of stars. And that's something which has been predicted in the galactic center. It should occur every 30,000 years if you look at solar mass stars. But in the meantime, we've seen probably the relics of the destruction of a big star. I mean, a sort of a very big star, like a giant star, where then the trails of that destruction sort of still orbit around and come back every few hundreds of years. And we, in fact, have been trailing the sort of little bits and pieces of this trail as it fell in, and used that, in fact, to as a test particle, if you like, to measure the density of gas around a big black hole. would have not thought that such a thing would have been possible. Right. So I mean, it's all kinds of things which you would initially just be very clear about. No young stars. Everything goes on a very slow speed. The only thing is sort of this old home folks in the center, and what you see is a lively star formation region, which is the most active star formation region in the entire Milky Way. That tells you how sometimes in astrophysics the N-body system can be so much richer than you would have thought.
Thank you very much for your very nice answer. And well, maybe a second question. So as you know, Einstein himself died without believing in black holes, right? I mean, he thought that black holes would not exist in physical reality, right? So and you have been the person that has, in a sense, proved experimentally Einstein wrong, right? So how do you feel about that? Would you like to comment about that? Just I mean.
Well, okay. Look, Luis, I don't know whether you've ever been to the Hebrew University and checked out Einstein's archives. If you're in Jerusalem, please do so. That's fascinating, because if they let you look at it, then you realize how hard this all was. I mean, you know, we all sort of grow up with this hero story, Einstein sort of thinking for 10 minutes or 20, and then coming up with a general theory, and absolutely not. The guy was suffering. The guy was making mistakes. His math wasn't good enough. I mean, in the Hebrew archives, you find a little booklet by Grossman, where he basically gave Einstein in I think it must have been around 1913 or 14, a little booklet, exercises in tensor algebra, you know, so that he could learn how to do tensor mathematics, because his mathematics wasn't good enough. And he was very honest about it. I mean, if you read him about this. So I think we sometimes, of course, we have made too much of Albert Einstein. I mean, his theory is fantastic, but you overtax someone. We all make mistakes all the time, and Towns did too. Towns is one of the great experimental Nobel laureates of the first rank. Still, he made mistakes. I mean, one shouldn't expect everything from geniuses.
Okay, thank you very much. It was just a kind of, to hear you talking about that, obviously. So we have a lot of compliments in the chat. So coming from people from our university. So thank you, Professor Genzel, for this very interesting talk, for this awesome talk. Congratulations for this wonderful webinar, etc. So thank you very much. So, but, well, I mean, we are coming to the end. Would you like to say, let's say, some final words to your audience before we close?
Well, I mean, of course, given the last few years and what we've seen in a country which we all have admired for its prowess in the sciences, and what has happened to some of our colleagues, and certainly the mood in the country, I can only say, and that's true for all of our countries, we have to convince people that science is something which must be done and is not arbitrary, and that striving for excellence in science is absolutely important, because only then can you really hope to get where you then, if you're lucky, might find something.
Thank you very much, Professor Genzel. I mean, it's been very inspiring and illuminating. Thank you very much for this moment. Before we close, I'll ask again everybody to turn on their microphones once again for a final round of applause in retribution for this wonderful webinar.